There is a type of rock in northern China that functions like a geological trap. During the dry season, it looks and feels like solid stone, layered cliffs hard enough to walk on, hard enough to build on, and then it rains. Within minutes of contact with water, the rock swells, fractures, and collapses into flowing mud. Not soft, slowly eroding clay. A dense, fast moving slurry that pours off the hillsides like wet concrete, stripping the gully walls bare as it descends. This is the Pisha sandstone, and it covers roughly 16,000 square kilometers of the Loess Plateau in northern China, an area about 10 times the size of Houston. Every monsoon season, the landscape dissolves, up to 40,000 tons of material per square kilometer, liquefied and flushed into the Yellow River annually. That rate of loss made this the most intensely eroded landscape ever measured on Earth. For decades, engineers tried to stop the bleeding with concrete. Thousands of check dams, rigid walls built across the gullies to catch the mud before it reached the river. The rock destroyed them. It dissolved their foundations, cracked their facings, carved new channels around the sides. The concrete lost. The solution that finally worked wasn't stronger than concrete, it was weaker. A thorny shrub, cold tolerant, fast growing, with bright orange berries planted by hand in rows across the gully floors. 2-year-old seedlings standing barely a foot tall. To understand why that worked, you have to understand exactly how the rock fails. Pisha sandstone formed across hundreds of millions of years, the Permian, Triassic, Jurassic, and Cretaceous periods, as layers of sand, shale, and mudstone compressed into stratified beds. But the compression was never strong enough. Geological pressure in this region ran low, and the bonding process that turns loose sediment into true solid rock barely completed. The result is a formation that looks finished but isn't. Structurally, it's closer to compressed powder than real stone. What holds it together, barely, is a matrix of clay minerals cemented between the sand grains. One mineral in particular dictates the catastrophe. This specific clay doesn't just sit passively inside the rock, it reacts with water, aggressively. When water molecules contact its crystal layers, they force themselves between the sheets through a chemical exchange, and the mineral swells, approaching 150% of its dry volume. The force of that expansion is enough to shatter every weak bond between the particles surrounding it. That number is the whole story. 150% volumetric expansion means the layer binding the rock's grains together doesn't slowly erode. It detonates. A rainstorm doesn't wash this rock away. It makes the rock blow itself apart from the inside. Once the surface disintegrates, the material is no longer stone. It's a slurry, heavy, fast, and loaded with coarse sand. It funnels into the steep gully networks that lace the plateau, narrow channels carved by centuries of this exact process, and accelerates downhill under gravity. As it moves, it strips away more exposed rock, which liquefies on contact, adding mass and velocity to the flow. The flow feeds itself. For centuries, a fragile mat of native grasses and root networks had shielded the sandstone from direct rainfall, absorbing the kinetic energy of each storm before water could reach the reactive clay. Overgrazing and agricultural clearing across the Loess Plateau stripped that mat away, and once bare rock was exposed to the monsoons, the destruction outpaced any natural repair. Each season removed more plant cover. Each season exposed more rock. Each season produced more mud. The system locked. Without roots to shield it, the rock dissolved. Without stable ground, roots couldn't establish. The landscape was actively maintaining its own collapse and exporting the consequences hundreds of kilometers downstream. For context, the Pisha sandstone area covers less than 3% of the broader Loess Plateau. It was generating over 70% of the coarse sediment entering the Yellow River. Because those eroded particles were heavy, heavier than fine silt, they didn't stay suspended in the current for long. As the river flattened in its lower reaches, millions of tons of Pisha sand dropped straight to the riverbed every year. The bed rose. Over decades, it climbed 13 to 30 meters above the surrounding cities and places like Cifen held between artificial levees, creating one of the most dangerous flood risks on the planet. A dissolving plateau was building a suspended river over the heads of millions of people. The erosion cycle that fed all of this didn't shut down between storms. It ran on three engines, and they took turns. During the 8-month dry season, winds scoured the exposed rock faces, loosening surface material and carrying fine particles into the air. As winter set in, water that had seeped into cracks during the last rain froze, expanded, and fractured the rock from within, generating a crumbling layer 5 to 10 centimeters deep along the gully walls. This was the ammunition. When the summer monsoons arrived, they didn't hit solid rock. They hit a pre-shattered surface, primed to dissolve. The monsoon rains in this region are concentrated and violent. Most of the annual rainfall lands in a handful of intense storms. The water hits the loosened debris, and the entire pre-shattered layer liquefies across thousands of square kilometers simultaneously. The resulting flows tear through the gully networks, scour the walls, collapse the banks, and expose fresh, dry rock underneath. That fresh rock will freeze and crack over the next winter and dissolve in the next monsoon. Wind prepares, frost fractures, rain destroys. The cycle resets, each pass cutting deeper. The response, for decades, was concrete. Build rigid walls across the gullies, force the mud flows to stop, let the sediment settle behind the barrier. Standard erosion control. It works in most landscapes on Earth. Here's why it failed here. A rigid dam absorbs the full kinetic energy of the flow at a single structural point. In a normal watershed that's manageable, the foundations sit on stable ground. The surrounding material holds. In Pisha sandstone, the foundations are made of the very rock that's dissolving. Pool water behind a concrete wall, and the ground beneath the wall starts to swell and liquefy. The dam sinks into its own base. Meanwhile, the abrasive slurry hammers the concrete facing, and the violent turbulence at the base scours the soft rock anchoring the sides. The flow either undermines the structure completely or carves a new channel around it. When a dam high in the gully network broke, the stored sediment behind it released as a single catastrophic pulse, increasing the downstream flood peak by up to 70% and obliterating every dam below it in sequence. And even if every dam had held, the economics were ruinous. The terrain is deeply fragmented with almost no road access. Hauling concrete, steel rebar, and aggregate into collapsing canyons across 16,000 square kilometers was logistically impossible. A single standard check dam can run upward of $100,000. The number required ran into the tens of thousands. The budgets never existed. None of it worked. The landscape didn't need a stronger wall. It needed something that never tried to stop the water in the first place. In 1992, a researcher named Cifen spent months surveying the wreckage of failed check dams across the Loess Plateau. She worked with the River Conservancy Commission, and the conclusion she reached inverted the engineering logic governing every prior attempt. The mudflows couldn't be blocked. Their energy had to be bled away gradually, not at a single point, but across a broad, permeable surface. Not a wall, a filter. The tool she proposed was sea buckthorn, a thorny, dense-branching shrub native to the cold steppes of Central Asia. Silver-green leaves, bright orange berries, tangled growth that crowds out everything around it. Not an obvious candidate for fighting liquefied rock, but its biological specifications match the failure points of the Pisha sandstone with a precision no manufactured material had achieved. The bare rock is highly alkaline, pH up to 9.5, with virtually zero usable nitrogen. Almost nothing can grow in it. Sea buckthorn bypasses that entirely. Its roots host colonies of bacteria that pull nitrogen directly from the atmosphere and convert it into soil nutrients, roughly 180 kilograms per hectare per year. The plant manufactures its own fertilizer in ground where fertilizer doesn't exist. And because the ground is fractured and loose, cracked by frost, dissolved by rain, held together by nothing, the shrub counters with a root system that works in both directions. A single mature plant drives a taproot 3 to 4 meters straight down to reach buried moisture, while spreading horizontal roots 6 to 10 meters outward through the debris. Those lateral roots continuously sprout new shoots, cloned copies of the parent, so a single planting becomes a connected underground web that physically stitches the shattered ground together without any replanting. Above ground, the branches grow into a thorny tangle nearly impossible to push through. By 1995, B's team began planting 2 to 3-year-old seedlings directly into the dry beds of active gullies in the Xizhao Gully system in Inner Mongolia. Not on the slopes, in the channels exactly where the mud flows ran. The seedlings stood about 30 centimeters tall, with stems barely half a centimeter thick. They were arranged in staggered rows perpendicular to the flow direction, packed as tightly as 8 centimeters apart, achieving densities of up to 20 plants per square meter across the channel floor. The mechanical logic is counterintuitive but exact. When a monsoon triggers a mud flow and the slurry hits the rows of interlaced stems, the vegetation doesn't try to stop it. The matrix is porous, water passes through, but in passing through, the flow is forced to navigate thousands of small obstructions. Each stem, each branch, each node of tangled thorns bleeds off a fraction of the flow's energy through friction. The cumulative resistance across the entire vegetative band is enormous. Flow velocity drops below the threshold required to carry heavy sediment. The coarse sand falls out of the water and deposits in stable, terraced layers within and behind the shrub rows. The filtered water keeps moving safely downstream. No violent turbulence at the base. No scouring eddies undermining the foundation. No rigid failure point for the dissolving rock to exploit. The energy isn't absorbed at one spot, it's dissipated across the entire depth of the living barrier. And because that barrier is alive, it does something concrete never could. When deposited mud buries the lower stems, the plant doesn't drown. It sprouts new roots directly into the fresh sediment, grows upward, and raises the effective height of the dam to match the rising gully floor. The dam gets taller as the sediment gets deeper. The cost ran to roughly $200 per hectare, planted entirely by hand with locally propagated stock. For an area the size of Houston, that comes to about $30 million. No machinery, no steel, no concrete. For the first 3 years, the gullies still looked barren, sparse rows of knee-high shrubs against a backdrop of dissolving canyon walls. From the surface, nothing looked different. But the real investment was invisible, roots threading into alkaline rock, bacterial colonies establishing, nitrogen accumulating in ground that had never held nutrients. The system wasn't just filtering sediment, it was rebuilding the chemistry of the soil itself, manufacturing fertile ground from sterile rock, one root system at a time. Everything depended on whether those 30-centimeter seedlings could survive 3 monsoon seasons in a landscape that had shattered reinforced concrete. The turn came around 1998, when the canopies of neighboring plants merged into a continuous thicket across the gully width and the root networks fused into a single stabilizing mat below. From that point, the same compounding logic that had destroyed the landscape reversed direction. Trapped sediment held water. Water-fed roots. Expanding roots stabilized more sediment. Stabilized sediment captured more water. The loop ran the same way it always had, each step enabling the next, except now it was running toward recovery. In the monitored test gully, the flexible dams captured over 90% of incoming sediment. The maximum recorded depth of trapped material reached nearly a full meter, rock that would otherwise have reached the Yellow River, permanently locked in place. The nitrogen pouring into the soil from the bacterial colonies transformed the sterile ground into something plants could use, and a native perennial grass colonized the understory on its own, without being planted, forming a dense secondary layer beneath the shrub canopy. Researchers eventually cataloged 15 separate species, establishing in the treated gullies double the diversity found under conventional tree plantings in adjacent areas. Vegetation cover went from near 0 to 95%. Surface runoff dropped by half. Annual soil loss in the treated gullies fell by 92%. But the sediment trapping was only the first problem the system solved. The trapped layers, threaded through with living roots, were absorbing water. Monsoon rain that once flashed violently down the gullies was now soaking into the deposited material and holding. Soil moisture in the treated channels measured twice as high as in bare gullies right beside them, 15% versus less than 8%. The filter wasn't just stopping the hemorrhage, it was building a water reservoir inside a landscape that had never held a drop. And then the oldest stands started dying. Around the 10 to 15-year mark, the earliest plantings collapsed. Canopies thinned, branches withered, root activity plummeted. Thousands of tons of trapped sediment, held in place entirely by living roots, sat on the edge of catastrophic release. The response was violent and counterintuitive. Engineers cut the dying plants down to stumps, 15 centimeters above the ground, destroying the entire above ground structure of the dam. Instead of killing the shrubs, this triggered an emergency growth response. Root systems exploded with new branching. Dormant buds along the stumps pushed out dense new canopies within a single growing season. The dam rebuilt itself younger and structurally stronger than before. A second threat arrived alongside the aging crisis. A wood boring moth native to the region, drawn by the sheer density of its preferred food, ravaged tens of thousands of hectares of mature plantings in the early 2000s. The larvae tunneled into the trunks and main roots, severing the plant's water lines from the inside. The outbreaks forced a shift toward mixed species deployment in later plantings, breaking the single species corridors the moth had exploited. The system needed human maintenance. It was never a plant and forget fix. But the maintenance involved pruning shears and labor, not cranes and concrete trucks. Across the broader watershed, the trajectory held. Between 1995 and 2020, the Hantaichuan Watershed recorded a 44% drop in total soil erosion and a 69% reduction in sediment yield. Today, over 1.5 million hectares of sea buckthorn cover northern China, and the berries the plants produce have spawned a secondary industry in juices, oils, and nutritional products, generating ongoing revenue for communities that a generation ago occupied bare dissolving rock. Those 30-centimeter seedlings, planted into dissolving rock at $200 per hectare, trapped nearly a meter of liquefied stone per gully section. They doubled the moisture content of a landscape that couldn't hold water, recruited 15 species into ground that supported none, and cut the sediment feeding one of the most dangerous rivers on Earth by more than half. The rock hasn't changed. The clay minerals still swell when it rains. The monsoons still come every summer. Nothing about the underlying geology is different. What changed is the surface, the thin, living layer between the rain and the rock. The fix didn't overpower the destruction. It matched the problem's own physics: flexible, where the rock was rigid; porous, where concrete was solid; alive, where everything else was static. The most severely eroded landscape on Earth didn't need a bigger wall. It needed one that could bend. If that kind of engineering is what brought you here, subscribe. More is coming. Is